All right, and so in this problem here, this is the relaxed length. So this is the relaxed length of the spring, and we're releasing it, right? So it's going to fall, right? Now, this is not the equilibrium position because the spring is not exerting any force. It's just subject to gravity. So this is going to be, what is the new equilibrium position of the simple harmonic motion that results from releasing the block? Okay, the equilibrium position is when the net force is 0. So we're going to draw the free body diagram, right? The equilibrium position occurs when gravity and the spring force are balanced, all right? Net force is 0. So in this case, the A is 0, and so the mg is equal to kx, and we want to figure out how much we've stretched. So just divide the k, and then the mass is 4, the g is 9.8, and the spring constant is 200. Okay, so 4 times 9.8 divided by 200 gives you 0.196. So that means from here to here is 0.196, because this is the relaxed length and this is the stretch relative to the relaxed length. Okay? What is the block's maximum speed? What is the block's maximum speed in the oscillation? So we're going to do energy between here and here. Now, we don't have a minimum height, so we'll just say we're going to use energy conservation between here and here to help us figure out. So we're going to say this is h equals 0, okay? And then we can talk about energy conservation between this point and this point, because we released it from rest. So this is the initial energy, this is the final energy, and those energies should be equal to each other. Okay, because at the equilibrium is when we have the max speed, right? Max kinetic energy is at equilibrium, therefore have the max speed. So we look at the initial energy here. Do we have any kinetic energy? No, we released it from rest, so no kinetic energy. Do we have any gravitational potential energy? Well, if this is h equals 0, we do have gravitational potential energy. For mg, this is m, this is g, and what's the height? 0.196. Because we're saying that this is h equals 0, the equilibrium position. Any spring potential energy? No, because the spring, at this point, the spring is at its relaxed length. It's not stretched at all, so the x is 0. So this is how much energy we start with. 4 times 9.8 times 0.196. That's going to be 7.68 joules. And then how much energy do we have down here? Okay. Well, we have some kinetic energy. So 1/2 m times v squared. Do we have any gravitational potential energy? No, because h is 0. Do we have any spring potential energy? Yes, because the spring is now stretched. What is the K? 200. And then how much is it stretched from its relaxed length? 0.196. So then you're going to set that equal to this and then solve for V, right? So you take that minus 0.5 times 200 times 0.196 squared. 2, and then square rooted. I get 1.39 meters per second is what I get for the speed. What is the amplitude? Well, it's never going to go higher than this point because we released it there. There's no way it's going to gain, like this is the max height it's going to be. So the amplitude is actually 0.196. So it's actually going to go down the max stretch because it's always going to go up and down the same amount around the equilibrium position. So this is going to also 0.196. And I know this is the max height because it has this much energy here. It's as high as it can go. It can't go any higher than that. How long does it take the block to reach the new equilibrium position from the point of release? Okay. So the time for the oscillation, we can't use kinematics because the acceleration is not constant, right? The spring force is going to vary as it falls. So the acceleration is not constant. Don't try to use kinematics on this. It's not going to work. Because remember, our kinematic equations only apply when the acceleration is 0. Acceleration is not 0 here. So I can't use it, right? Sorry. Only apply when the acceleration is constant. Acceleration is not constant here. Okay, so to reach this new equilibrium position, we have to think about the period. We know the period, the period is one whole cycle. It goes down and then all the way up. Okay, so that means to go from top to bottom is half the period, and that means to go from here to here is a quarter of the period. So it's a quarter of the period, and the period is 2 pi root m over k. So that's going to be pi over 2 times root, what's the mass, is 4, k is 200. So it's going to be pi divided by 2 times the square root, 4 divided by 200. And I get 0.22 seconds. How far would the block fall relative to its initial position before its direction is reversed? Okay, so you just look at this picture. It's going to reverse directions right here. It's going to be twice this. 2 times 0.196 is going to be 0.392 meters.